In this video, I'll talk through the Advanced Higher Chemistry Unit 1 Chemical Equilibrium topic. By the end of this video, you should be able to write an equilibrium equation for a reaction, be able to calculate the value of an equilibrium constant, and also explain the effects of temperature and a catalyst on the equilibrium constant. This topic is building on the equilibrium topic from higher chemistry. Some of the key points that we need to know from that include at equilibrium, the rate of the forward reaction, rate of the reverse reaction, concentrations of the reactions and products remain constant at equilibrium. Le Chatelier's principle states that if a system at equilibrium is subjected to a change, the system will adjust to oppose the effect of a change. The position of equilibrium is affected by changes in different factors, including concentration, temperature, and pressure. Pressure for dealing with gases. A catalyst only affects the time it takes to reach equilibrium. It doesn't affect the position of equilibrium. Into the advanced higher content, we will be dealing with an equilibrium constant, capital K. This gives an indication if we favour the forward reaction or the reverse reaction. If we have the equation for a reversible reaction, the equilibrium constant can be calculated using this. It is found in the data booklet on page number 4. The squared brackets are the concentrations of the different chemicals. The other letters are from the balancing numbers in the equation. One of the things you're quite often asked to do is to write an equilibrium equation for a reaction. If we were given this one, where we have ozone and oxygen in an equilibrium, the way it's going to work is capital K equals, there's going to be the concentration of the oxygen, which is on the right to the power of 3, but the O3 in square bracket. Good. This one here, we're going to get 3 chemicals involved. We're going to have the right hand side to the power of 2 divided by NO to the power of 2 and just the C2. That one. This one here, got the hydrogen iodide on the right hand side, so it's concentration of that squared divided by concentrations of the other 2 chemicals together. Other things we need to know about is that the value of the equilibrium constant has no units. When we come to our calculation, we don't want to put any units at the end. If you're dealing with a solid or a liquid, that has a value of 1 and it's often omitted from the equation because it's not going to have an effect on the values. The position of the equilibrium can be determined from the value of the equilibrium constant. It comes down to the fact that we're dealing with the reactants turning into products. When we're working out the value of K, it's the products divided by the reactant. If the value of K is greater than 1, this must mean we have more products than we do reactants. That means that the position of the equilibrium is to the right hand side. If the value of K is equal to 1, that means that we're not favouring either side. It sits in the middle. If it's less than 1, that means that the products are smaller than reactants. The position of equilibrium is to left. Sometimes I find it helps to put numbers in when you try to work out what K shows you, remembering that it's products divided by the reactant. When it comes to factors that affect the equilibrium constant, temperature is the one we're going to focus on because it is temperature dependent. If a reaction is endothermic, increasing temperature will increase K. The reason for this is that endothermic reactions cool down their surroundings and they're favoured by the higher temperatures that we've got. If it's favoured, you're going to have more of the products, and because K is products divided by reactants, top line is going to be bigger, and that's going to increase the value of A. If you have an exothermic reactions release energy and heat up their surroundings. Well, increasing the temperature is not going to favour that. Because exothermic reactions are not favoured by the higher temperatures, that means you have less product, a smaller top line, that's going to decrease the value of A. When it comes to catalyst, the catalyst will not affect the value of the equilibrium constant. You might get asked to calculate the values of each chemical at equilibrium and then go on to calculate the value of K. Example would be where you're given an equation, we're told information about how much of a chemical we have at the start, and also some information about what we have at equilibrium. And what we need to do is figure out how many moles of each species will be present at equilibrium. What I find it's quite useful to do is to sketch up a little table that has different chemicals, and we plug in information about what we have at the start, and then what we've got at the end of equilibrium. If we've made 0.43 moles of hydrogen, we must have made the same number of moles of carbon dioxide as a 1-to-1 ratio. And if we've made that much of those chemicals, we must have used up the same value of carbon monoxide and water because it's all 1-to-1 ratios. And from here, if we had 1 mole of carbon monoxide at the start and we used up 0.43 moles, at equilibrium we'd be left with the difference between both of them. This one, all the numbers are 1-to-1 ratio, which makes it quite straightforward. I then plug in the numbers and I get out at equilibrium, those are the values of the 4 chemicals I must have. Next we'll go into some exam style questions. In this question, we're told information about the equilibrium mixture. We're asked to write the equilibrium equation first and then calculate the value of it. First thing you need to figure out is the balanced equation for this reaction. We've got hydrogen and nitrogen joining together to make ammonia. This isn't balanced, so we'll need to put in balanced numbers so we have the same number of each atom on each side. Then from here, we go back to the data booklet. We're using our K equals relationship from the data booklet, popping in the values, then get the concentration of ammonia squared divided by concentration of hydrogen cubed times the concentration of nitrogen. Next then, we need to calculate the value of K. We just need to substitute in the values because we are given the equilibrium mix. That gives us our 0.00272 squared divided by 0.1207 cubed times 0.0402. Popping that all into your calculator, give you an answer of 0.105. It is an equilibrium constant, therefore there are no units required. Next question, we're talking about caffeine being removed from coffee. They're asking us about which thing will change the value of the equilibrium constant. Equilibrium constant is temperature dependent. In this one, we're given a diagram representing an equilibrium. We're asked to calculate the equilibrium constant for this system. We need to look at the concentration in the hexane, which on the right hand side, divide that by the concentration in the water, so the aqueous solution. 13 particles in the top layer and 6 particles in the bottom layer. 13 divided by 6, which gives us 2.17. Again, no units, equilibrium constant. And this one, we're dealing with sulfur dioxide and oxygen reacting together. Which line is correct if the temperature of the mixture is increased? It gives us the value for delta H, which is the enthalpy. It's negative enthalpy, therefore it's exothermic reaction. If we're increasing the temperature, it will not favour the exothermic reaction. It would favour the reverse reaction. Similar to previous questions, if your equilibrium is shifting to the left and it's products divided by reactants, that means that your value of K will get smaller. Because we're favouring the reverse endothermic reaction, the concentration of the SO3 would decrease. So both of the values would decrease because of the way it's set up here. If it was swapped around, if it was endothermic forwards, that's going to all have an effect. In this question about dinitrogen tetroxide, we're asked about the equilibrium constant. Get the equilibrium constant, we're going to need to have the values at equilibrium, which we don't have yet. Setting up my little table like this, we'll get 2 chemicals here, so it might be a wee bit more straightforward. We know what we have started with, and we know what we've got at the end. Difference with this one is a 1:2 ratio. So if we're making 0.24 moles of NO2, we would have used 0.12, half of that, moles of the N2O4. And that means at equilibrium, the difference between them will be what we'll be left with. Start with 0.28 and we've used 0.12 moles of that. And that means then that if we make up our equilibrium equation, the right hand side divided by the left hand side, remembering to square the right hand one, pop in our numbers that we just figured out, pop in our values from before, that gives us 0.36 as our answer. There was then a follow-up question to this which says that at 25 degrees, the value of the equilibrium constant was then 0.12, and we have to explain whether the forward reaction was endo or exothermic. Yeah, so we're going to bear in mind that it's products divided by reactants. Decrease in temperature has caused the value of K to go down. Decrease in temperature favours the exothermic reaction. The reverse reaction is exothermic, so the forward reaction has to be endothermic. We could have looked at it the other way. We increased temperature, so going from 25 to 127, the value of K has increased. So then increasing the temperature has favoured the forward reaction because we have more products, and increasing temperature favours the endothermic reaction. Hopefully by the end of this video you're feeling a bit more comfortable with writing the equilibrium equations, calculating the values of equilibrium constants, and explaining the effects of temperature and catalyst on the equilibrium constant. Thanks for watching, goodbye.